All right. So today, all we're going to do is we're going to talk about the Poisson distribution, um, and it's going to be very broad strokes. We're not worrying about interpretations and things, just kind of conceptually what it is, what it's used for, and things like that. And then we'll talk a little bit about making tables, which is something somebody had asked for specifically. Uh, and so this first bit of the script, you don't need to worry about, just run through it because basically it's just making this plot that we'll talk about. And so for the Poisson distribution, this is what the graph looks like. The components of a Poisson distribution is that it's a count variable, which means that it cannot be a negative number. It must be only positive whole numbers. The occurrences of whatever event you're observing have to be independent from one another. So an occurrence happening doesn't make it any more or less likely that it will or won't happen again. And you know the average response of the average occurrence, the average rate of something over some unit of time. So for instance, well, first, note that if you recall from the binomial problems that we worked on with logistic regression, that maximum likelihood is a function of two probabilities. It's the probability of A times the probability of B. But in this case, with the Poisson distribution, we don't have that second probability. So if you remember Patrick's example of the coin flips and saying, like, all right, what's the probability of getting 4 heads out of 10 coin flips? Like, that logically necessitates the probability of 4 heads and the probability of 6 tails. Like, that's just how it works. But with a Poisson distribution, it doesn't necessarily work that way. So let's say, for instance, that we're looking at like the number of letters you get in the mail on average, every day. And if what this chart where it has this lambda, that is your average rate of occurrence. So if you average getting 1 piece of mail per day, you're looking at this first red distribution. If you average getting 2 pieces of mail per day, then it's the second distribution. And what you can see is as the rate of occurrence goes up, that distribution slides down the axis and kind of looks more like a normal distribution. And basically, like I said, you can't get a negative amount of mail. So it's bounded by 0 on that lower end. And so if you average getting 1 piece of mail per day, you might get 2, you might get 5, you might, something happens in one day, like you get boxes and boxes of thousands of letters. Like, that's possible, very improbable, but it's possible. But it is impossible to get negative mail. And so as far as, just one thing to note, as far as these distributions like looking kind of blocky and not smooth, like, that's just a function of the way this distribution works and the way that it's actually plotted, because I only specified up here in making these things the x values of 0, 0, 1, 2, 3, dot, 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 dot. Because if we would have used decimals, then anything that's not a whole number gets zeroed out anyway. So it's kind of a wonky thing about this distribution. So don't worry about the fact that it looks like it's flat up here. Just imagine that they're the normal peaky, smooth line type curvy things. But we'll work through all this and how it works. But if you have some average rate of occurrence over some period of time, so whatever your thing is, if you're talking letters per day in the mail, then how many letters in this 24-hour period. It could be your unit of time could be per week. If you're talking about like how many times did you have thoughts about such and such this week. It could be per minute and like how many blinks per minute. So whatever your unit of time is, it doesn't matter, but you have some rate of some event over some period of time. So lambda, which you'll sometimes see as a lowercase r for rate, is that average rate of occurrence over whatever your unit of time is. And so if you're looking at the probability of observing x number, well rather k number of events, then this right here is the formula for how you would calculate that. So basically, if you are looking, if lambda is 1 and you're looking at this first line, what's the probability of getting 2 letters in a day? Well, you would plug in all the information over here, and k would be 2 and your lambda would be 1, and you would calculate all that out. As far as r goes, this e up negative, or e to the power of negative lambda is just the exponentiate negative lambda. And as far as the factorial down here, in R you just specify that as factorial k, since the exclamation point in R specifically means negate. And so I want to run you through an example that I think is kind of fun. And we're not going to talk about all this code up here. If you want to ask questions about it later, like, we can come back to it. But all you really need to know is that what this is doing is it's taking, there's this archive that has all of Donald Trump's tweets, plus it has all his associates and all that. So there's a lot of Twitter information in this particular archive. And what this code is doing is taking all the tweets between 2016 and 2019 and scraping them and extracting them into a data frame. So we have 11,042 tweets, where it has the source, the text itself, the date and time it was created, how many retweets it had, how many favorites, and then over here you can see where it says is retweet. And so later on down here I actually filter out retweets and stuff like that. But basically, so this just, all I did here is I created all tweets, which is a data frame that contains all of Donald Trump's tweets from the real Donald Trump account, not his POTUS account. And so I just created a data frame with all of his tweets. And then here I'm just specifying 3 dates of interest that I want to plot. The day he was elected, the day of the inauguration, and the day that the Mueller special counsel was announced. And then here I'm just specifying a key term. The key term is fake news. And what we're going to do is we are going to look at the rate of occurrence of fake news in Donald Trump's tweets and plot it out. So when we run this next line, here's what it looks like. So this orange line is the inauguration date that we or the election date that we specified. This blue line is the date of inauguration that we specified, and this black line is when the Mueller special counsel was announced. And these are just counts of by week, how many times did fake news appear in Donald Trump's tweets. Now the fun things that you can do with this is that, like, you can change this and make anything your key term. If we want to see how often the word sad appears in Donald Trump's tweets, we can do that. If we want to change the dates of whatever we're doing, you can just keep playing with this and do all sorts of stuff. But for now, we're going to stick with fake news. And we see that, there's a pretty high weekly occurrence. So if weekly is our unit of time, then we would want to see, like, on average, how many times per week does Donald Trump tweet about fake news. And so with this next chunk of script, All we're doing is we're summarizing to get the weekly statistics. So for the week of January 22nd, 2017, he had a total of 28 tweets, one of which mentioned fake news. The following week he had 46 tweets, two of which mentioned fake news, and et cetera, et cetera. So now we have this data frame of the weekly summaries of total number of tweets, and how many of those had the text or fake news. And so now if I just take the mean of that, the target variable, which is the number of occurrences of fake news, and I'm just going to store that as lambda, we see that on average 3.11 occurrences, 3.12 occurrences of fake news per week. So that lambda value, our average is 3.12. So then we can ask, well, what's the probability that in any given week Donald Trump is going to tweet about fake news 5 times? We know that on average he tweets about it 3.12 times. So what's the probability that he's going to tweet about it 5 times? We plug in all that information into this formula, and our K is 5, which is the number of occurrences that we're wanting to see. 3.1 is the average rate, and when you calculate all that out, you get 0.107, so about 11%. There's about an 11% chance that we will hear Donald Trump tweet about fake news 5 times in any given week. When we plot that out, all I've done is I've taken that same plot from before with all the things, and I just specified only one value of lambda, which is the actual, that 3.12-ish. And so when you look here, you can see that this is the probability of 5 occurrences right here. If we follow that up, it's right about here, which we can see is right about 11%. The probability that we'd see 7 tweets in a given week about fake news is going to be somewhere around 2.5%. The probability of him being able to refrain from tweeting about fake news for a full week is less than 5%. There's a less than 5% chance that Donald Trump will not mention fake news for an entire week. So as far as like how that works, like what that can tell you with your research, is you can imagine having the same thing where you have some kind of count outcome. Perhaps it's the number of suicide attempts. Perhaps you're looking at some particular thing, and in some population you're looking at teen pregnancy rates or whatever. And these are typically low occurring phenomenon. And so if you have some other variable that you are now able to use that and include that as a predictor, what you can look at is you can see like, okay, well, does this particular variable systematically change the probability of observing whatever outcome? So if it's suicide rates, if I add gender as a predictor as well, like I can see, like, are males more likely to, have suicide attempts than females by looking at those probabilities this way? Perhaps it's the teen pregnancy thing, and you're looking at whether or not they participated in some program, and so you can look at or the length of time and as a continuous measure, and like. At what point does this become systematically different, such that it's not just random chance and there is differences in these things? For instance, down here I just have some stuff that if we break this down instead of weekly, this just breaks it down daily, and then I'm going to add a factor that just specifies like what day of the week that is. And now summarized by that, and we can see that on Mondays and Wednesdays seems to be when Donald Trump tweets the most about fake news. here I'm just coding it by, I'm calling, if it's Friday, Saturday, or Sunday, I'm coding it as a weekend, and otherwise coding it as a weekday. And we can see that, it's about 50% chance during the on a weekday, and only about a 40% on weekends that he does this. And so point is that if you are doing some sort of analysis with this, it's just like what we've done before using GLM, only now instead of family being binomial, the family is Poisson. And the default link there again is the same as the binomial. It's that the log. And so if we run two models just predicting target, which is the number of fake news tweets by day of the week, and then this one is just by that weekend variable. When we look at day of the week, since our contrasts are coded with Friday as the reference group with all these zeros, when we look at this, like we can see there's not really much of anything there. There is this, finger quote, marginally significant that, it seems like on Monday the chances are a little bit higher of seeing about tweets relative to Friday, since Friday is the reference group, but nothing really to see here. And then if we look at weekend versus weekdays, we can see, that, oh, look, there is this significant difference here. And, blah, blah, blah. The rest of it basically works the same. And so, like I said, I don't really want to get into like interpretations and things. I just want to make sure that everybody knows like what this distribution is for, that it is for count variables. It's especially useful for rarely occurring events. So does anybody have any questions about that before we talk about tables for a little bit? Does that make sense at least though? And now does this graph up here make a little, or does this part make sense? And also why, like if you're looking at this one, if the rate is only 1, it can only go one direction. But as you slide up, now you have more room to wiggle around that mean, which is why that the distribution changes as your rate changes. But that's the gist of it. And so just know that's a possibility. And if you're working with something and you think that you might need to be using this distribution, then at least and you can go look it up to figure out, like, all right, so how do I actually interpret these things, and blah blah blah. All right, so moving into tables, there's a couple really nice things about being able to make good tables. One is that it makes things very easy for the reader when you can have tabled information that's laid out in a logical, straightforward way that's easy to extract the information that you need. A more practical benefit of table is that oftentimes manuscripts that have word limits will say something like, 5,000 words, not including abstract tables or references. And so the more information that you table, the more words you save to actually be able to talk, because once you table information, you don't give that same information in the body. You just refer to the table. As shown in Table 1, there was a significant difference between A and B, but like you're not reporting the actual statistics again, because the actual statistics information is in that table. And so today we're mostly going to just be talking about some of the considerations of informative tables, and we'll do one like very simple, straightforward example, and then one that's a little bit more complicated. That the first one is easy enough, and then the second one there's more than we possibly could talk about. We've mentioned it before with Stargazer before, but I want to show you all some other stuff with that. So if we just want to make a descriptives table, going back to the MT cars data set, we haven't used this since the beginning of last semester, where it's broken down by miles per gallon, cylinders, and make, and manual versus automatic transmission, and blah blah blah. And so basically, like, we just want to make a descriptives table of the miles per gallon, broken down by manual versus automatic transmissions and how many cylinders it has. So just using the summarize function, I create like the basic structure of the table that we're looking for, where we have the manual transmissions and or is that the other way? And then the automatics. And then for 4, 6, 8 cylinders, blah, blah, blah. So now we have this data frame. And then all I'm going to do is take that T1 table and write it as a CSV, because now I can open that. It just writes right to your working directory. So now I have my cars table.csv. And I have the basic stuff that I need to start working on my table. Now, as far as tables themselves, it's a lot like, first of all, if you haven't ever actually read the APA manual, I would really suggest at least reading through each of the sections fully. It has a lot of information here about the tables and how they all work and what you are and aren't supposed to do and blah blah blah. But especially like when it comes to how you do like your column spanners and things like that, and all these column heads. But kind of the way that we've talked about with graphs, and that there's any number of ways that you can do things, and it really comes down to, well, what is it that you're trying to show? What comparisons are you trying to make? There's an infinite number of ways to do any given table. But for instance, I wanted to show you an example here. This is a table that was in my thesis, where I had this primary sample versus secondary sample. And what that was that like there was a total of 335 in this primary sample, but there were a bunch of people that I excluded for reasons like failing attention checks and things like that. And like I said beforehand, that I will liberally be excluding people for these various reasons. And so then I had this other sample that had only 287 people. And so I wanted to be able to show the descriptive statistics for each of these things. Like, this is all the statistics that are relevant to the method section of this manuscript, broken down by both the primary sample and secondary sample, so that the reader can see like whether or not there was a big difference between the samples themselves. And so for this particular table, I wanted to break it down by having these two separate columns. And then also for all the variables that of interest in the model, like the means and standard deviations by sample. The cell count is something that's often overlooked in our field, unfortunately. And one thing to keep in mind is that, especially now with the ability to do online supplementary materials, it's over-reporting is better than under-reporting, because maybe 97% of people don't care about what your actual cell counts were when it's broken down by two separate conditions. So I had one manipulation where I was manipulating this thing over here, and one where I was manipulating this. And so most readers might not care about what the actual per cell count was. But who knows if, a few years down the line, somebody's rolling through trying to do a meta-analysis that's related to construal level theory, or maybe they're doing a meta-analysis related to self versus other focused values. And without having those, cell counts, that could make it to where they can't get the information that they need to calculate the specific effect sizes for like some particular group of interest or whatever. And so, but again, like this particular table all came down to wanting to show all the information for like this sample as a whole versus once I exclude all these people out here. The things that are always going to be the same in any APA table, like up at the top, you're going to have your table number, your title. Table title is the next line and it's italicized. And then you'll always have a spanner bar beneath that. Note that there's a little gap here between like column spanners, that's not just another continuous table spanner. Down at the bottom, there are 3 different types of notes, where you see note italicized followed by a period. That's called a general note. And then there are specific notes, which a specific note would be if you have some sort of superscript up here. So say, for instance, on one of these, I just had, an A for something. And then down here, your specific notes will indicate what any type of additional superscript annotations you put in your table. So then down here, I would say A and blah, 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 whatever that note that I annotated up here, like that's called your specific note. So that will go underneath on a new line, so you wouldn't just add it on here and continue with having that superscript A. And then below that is your probability note, which is the standard thing that you see where it'll often have, 1 star, P is less than 0.05, 2 stars, P is less than 0.1, whatever. And so that is the specific order of those notes. Your general notes, which anything that's not common, but if you abbreviate anything, that's something that you annotate down in your general note. Things like M and SD, obviously you don't need to say like what common statistical abbreviations mean. And here's another example of a table that it was a series of nested regressions where I had 3 nested models for each of 3 separate, financial strain variables. But this was just a nice way to be able to lay it all out where we can compare across all these models and see how things differ. If anything in your table, for instance, if you're looking at regression tables specifically, make sure that you have inside the table notes how things are coded. So whether it's construal, I had dummy coded it as 0 and 1, so I specify what 0 means and what 1 means. If it's effect coded or if it's contrast coded, you would specify like how these values are coded, because without that information of how the data is coded, you can't interpret these tables. And so that said, coming back over here to this table that we just made, as far as now that we have this bare bones of a table, and yours may differ as far as not being on a Mac, but start by rounding these off to 2. And so now we have, there's any number of ways that we could lay this out. We could leave it like this and have the manuals over on top of the automatics, or we could say take these and move them over here, and in MSD Let's move that over. Let's delete that stuff. Let's delete these. And we don't need these anymore. And so now on your column headers, those are centered. On these, different strokes for different folks sometimes. There's actually a way that you can decimal center values. I'm not going to get into all that sort of stuff, but anyway, point is that now we'll come up here and we'll say that these are, automatic, and these are manual. Collapse this down. Now notice that I left this extra column in here because now when we go back in to start adding all of our lines, and we'll come up here, and this would be table 1, whatever title you want. And then I'm going to delete these cells to just shift everything over. Now from here, making tables in Excel is all great and grand. Where the real pain comes in is moving it over into Word. So there are some things that you can do at this point in the process that are going to greatly help with that part of the process. For instance, merging all the cells that need to be merged. So with these, I just merge all the way across. So once I move this into Word, like this is just one big row, and it's not going to get all wonky with trying to adjust different cells. We also need a bar down here at the bottom. We'll need a bar up here under this. And then down here, also merge your notes. If you have like specific notes or probability notes, go ahead and add those, like again, merge those cells. In this case we don't, but this would be note, whatever you have. And so now you have like the basic setup of your table. If you want to save this, make sure you don't save it as a CSV. Save it as Excel, as we learned last semester when we formatted tables and then turned around and saved them as CSVs and lost all our formatting. But in this case, now if I just take these and move over into Word and copy and paste, one of the reasons that Word is such a pain is just because it gets real finicky with when you're adjusting your cells. What I do to negate that is I'll go to select the table, and I'll go to like my table properties, and in the cell options it has this automatic padding stuff, and I will turn all of this down to 0, and now it will allow me to adjust my column widths without without doing crazy auto wrapping stuff. For instance, if I come up here, let's see if I can. Well, I'm sure once you start making your own table on anything, go ahead and try adjusting your cells, and you'll quickly see that Word is a pain. But anyway, once you make that into adjust that padding stuff, then it's not a problem anymore. And why did this not copy my cylinders? Oh, it did. but it's just because I didn't. There we go. So then coming in here, and one nice feature is if you look under your table layout, you can click on grid lines, and now you can actually see your margins. So as you're adjusting things, you know, you can get whatever kind of spacing you want or need. Sometimes using this over here is nice. Other times that's going to completely screw up your whole table. It can be real finicky and terrible, be sure. And I hate Microsoft Word. But anyway, point is that by having, like I said, over, notice how up here, like it recognizes this all as one cell, and so it doesn't try to do this stuff where you know, it holds certain columns, certain widths, and expands others, and blah blah blah. So by setting it up as close to what you want as possible in Excel ahead of time, it makes it a lot easier on the back end, and you know, that's good enough for now. As far as making a nested regression table, this is something that's much more difficult. And so all I'm doing is I'm predicting miles per gallon by cylinders, and then also the interaction of cylinders and horsepower. And we look at our model summaries and we say like, oh yeah, blah blah blah, and then we do our model comparison and we see P is 0.04, so including that interaction did significantly reduce the error, which this information is something that you might also want to put in your table. And so going back to this stargazer thing that we talked about briefly last semester, as you can see when you look at this help, like there is a lot of things that you can specify, and far more than I even understand. Like I just figure out what I want to show and then start looking through and say, okay, how can I get it to show this? But you'll see that I have two things. The only difference between these two is that on this one it says type equals text, and on this one it says type equals HTML, out equals modtable.html. So this text, and when you don't have an out, what that does is it displays your table as it will output here in your console. So starting by using this text to go through some of these things and build the basic table that you want, and then later we will change the type to HTML and give it an out equals, and that's specifying you're naming a file and you're exporting a file, and I'll show you what that does. But anyway, so as we're looking at this part up here, for instance, you know, digits equals 2. I mean, you can just play with this and see that if we change that to digits equals 3 and run it, that now it rounds it to 3 digits instead of 2. So it depends on the level of specificity that you're looking for. For the star cutoffs equals, if I comment out that so it just doesn't run that line, one thing that really frustrates me is that like it'll annotate 1 star by default as P of less than 0.1, and 2 stars P of less than 0.05, and 3 stars is P of less than 0.01. And like I don't like, you know, this less than 0.0 or less than 0.1 being, you know, a star. So here I just changed it and I told it that I want the stars, 1 star to be 0.05, 2 stars to be 0.01, and 3 stars to be less than 0.001. For the covariate labels thing here, all that's doing is you can specify what you want the rows to be labeled. If I take that one out and run it again, by default it gives me like whatever the R output tables are. The column labels, that's this up here. So I specified model 1 and model 2. If I take that one out and run it again, Oh, it's because I'm on the wrong one. There. There we go. So, like by default, like there are no column labels up here, and so I wanted to label, model 1, model 2.
What is CI equals T? Is
Yeah, that's the confidence interval. So by default, if you take that out, instead of getting a confidence interval, it's going to give you just standard error underneath. But by telling it CI equals true, when we run it now, it will give me the confidence interval underneath. There are arguments that you can put in about the confidence interval that you can specify if you want something besides the default 95% confidence interval. You can specify even down to like what the separator is here. So is it a comma that's between the lower limit and upper limit intervals, or is it some different character? If for whatever reason you want like a slash or whatever. So anyway, point is that you can play with all this stuff, and Stargazer does stuff besides model tables. You can also do summary descriptive statistic tables and things like that. But that's something that you'll just have to kind of, if you just look up Stargazer on Google, like you can find where people show how this other stuff works. But point is that we now have this table, and we'll say that this is the table that we want. So now down here on this next line, I change the type to HTML, and I tell it out equals mod table.html. And when we run that line, it looks like a bunch of gibberish down here, which this is what it'll look like whenever type is HTML instead of text. But none of this matters because we have an out file here. So we exported a file. And if you look over in your working directory, week 8, I now have modtable.html. Now the beauty of this is that this recognizes the actual cells. In other words, if you just copy and paste this entire thing into Excel, you now have everything in their appropriate cells, and so you can start from here as your starting point of making this table pretty now. So for instance, one thing is that one of the first thing that I would do is, confidence intervals aren't typically in parentheses, they're in brackets. Well, that's an easy fix. You just select all those, and you're going to do a replace and find an opening parentheses and change it to an opening bracket and click replace all. And then change your closing parentheses to a closing bracket and replace all. And now all of those parentheses have been changed to brackets as they should be. You've got some extra stuff that you can, extra rows that you can delete and whatnot. Delete that, and then we'll come up here and we'll insert, table 1. We don't need that. Now, as far as this goes, you have your model information up here, and or the parameter information up here and the model information down here. So it makes sense to say throw in a bottom border down here to separate those things. We'll throw in a bottom border down here. That probability note will be on its own line. Up here we have bottom border. Up here on these things, they'll be centered. Now here I'm going to insert a column between these two and pull them down, just because now whenever I put in that bottom border, it leaves that gap between them as it should be. And if you didn't put a column between that, it would just look like one continuous line between the two cells. And then let's say we want to center all this information. Now down here, you can change some stuff like observations, just make it N. But in this case, notice how the N is the same for both of them. So it's redundant information. So we probably don't even want an N row in this table. Instead, we're going to add that down into our note. N equals 32. And now we don't need this. We have our R squared, adjusted R squared, and that. Here, probably just clean this up a little bit, and why it outputs a semicolon, I don't know. But this will change to F and then DF so that the reader knows what it is that we're talking about here. And again, just kind of cleaning this up a little bit to make it the normal kind of thing. Move that up. Let me take that line back off because I'm going to add a line below that. Change this to RSE. Change this to just ADJ period. And then like here for this mod compare thing, that's where we have this information about the model comparisons. And so we'll paste that in here. Add in our bottom border. And we don't need this row. Alright, and then so here you would specify like CYL equals number of cylinders, mod compare compares, mod compare tests for significant reduction of error in nested models, blah blah blah, whatever the case is. And then format, wrap these cells. Merge them together. Down here, merge these together. Up here, merge these together. That one's already merged. And now again, we have the basic table, and so we can come over into Word and paste it over into here, and now start with adjusting all your, see this kind of stuff that like as things get wonky, but if you instead like change that default cell padding, it makes it a little bit easier to be able to come through and I can't spell, and adjust from there. But point is that as you work through all of these tables, like now the nice thing that you have this, then in your results section you don't have to give any of this information. Like all you're doing is referring to this table. So your results section, instead of being this huge massive paragraph that's full of all sorts of statistical information and stuff, it says as shown in table 1, like blah blah blah, and you just talk about the effects, like you're not reporting the actual numbers, and like you have your model comparison, so you don't have to give this information in line in the text. You can just say that like a model comparison showed that model 2 significantly reduced the error, and leave it at that, and it's less words that you're having to put in the body. and so just saving that for, more important words. But again, like anytime you're doing any sort of tabling of stuff, anytime you're doing any sort of tabling of stuff, it's kind of, like I said, it's kind of like the figures, that it really just comes down to what is it that you're trying to show in this particular table. The other things that like you'd have to do here is go through and adjust things that should be superscripts, like make them superscripts in the table. All statistical abbreviations would be italicized, so you're going to run through all those. And again, definitely read through the information that's in the APA manual. It even gives like the common known type things and the proper way to abbreviate them. But point is that there's really 3 steps of the process of making tables. One is making your bare bones basic table in R, and then exporting something to Excel, where there's where you're going to be able to much more easily work with it and make it pretty. You want it to be as close to the final product when it leaves R, so that it's less adjusting on the front end or on the back end. And especially when it comes to like the very, very, very last thing that I ever do in a manuscript is actually make the tables, because the last thing you want to do is export this table, sit here and go through all this work to, change your parentheses and this and this and this and move all this around, and then you rerun your analysis later and it's all changed and you just have to do it all over again. So you basically make your table in Excel, and then you'll just copy and paste that over into Word, and then deal with Word's crap of like now trying to adjust it all to make it fit on the page. One thing that I'll also point out is you'll notice that this table is too wide for a page. And so we had to do a horizontal page here. If that's the case, if you need a horizontal table, then what you have to do in Word is add a section break, kind of like a page break, where you would just say at the bottom of this page, insert break, and it'll be a section break instead of a page break. And then now that I have a new section in Word, I can turn just that one page horizontally, and then after this page insert a new section on the next page, and now back down here change the orientation back to portrait. So that's another thing that can be a huge pain when you're working with tables, is trying to get it to display within your margins essentially. Does anybody have any questions? Cool. Well, I have this digital copy of the APA manual, and I keep it in a very quick and easily accessible place because I use it all the freaking time. And if y'all want that digital copy, you can shoot me an email, and I'd be more than happy to send it to you. But if nothing else, then I'll see y'all next week, maybe. I don't